Hello, welcome to our next set of algebra notes. We are on Unit 2, Outcome 9. This is the last section for our Unit 2, so we're getting pretty close to our Unit 2 exam. That should be coming up. Make sure you're getting ready for that exam. Make sure you're doing the practice exams. They're available in my lab. We've got both the, printout one that's paper and pencil, similar to the test, and then we have a built-in practice one into my lab that you can do over and over again. It's in the where you find the assignments or the homework and quizzes and stuff like that. So make sure you're getting that practice test and getting to it and doing it so you're getting ready for the exams. Make sure you finish all the homework and quizzes for Unit 2 and get ready for that second exam. It's coming up here fast. So this last section of Unit 2, we're going to change gears a little bit. We're going to deal with some rational functions. We've seen some rational expressions and stuff earlier. This section we really want to get into the idea of how to graph rational functions, what their graphs look like, and the properties they have. Because rational functions have some weird properties. They do some weird things. First thing, whenever we dealt with any kind of rational function, we've always had to worry about the domain. We worried about the restrictions, the values you're not allowed to use for x because you might divide by 0. And that's going to be true here too. So they're going to start off this homework and we're going to start the section thinking about the domain of these rational functions. Remember, the only things you have to worry about are dividing by 0 or square roots and negatives, because since we're doing rational functions, we're really going to be worried about dividing by 0. So I have to look at these and think about what numbers could I plug in for x that would make the bottom equal 0. Now this one's nicely factored, so it makes it pretty easy. I just think about what would make the bottom 0. Well, here you can see that negative 5 plus 5 would be 0. So we can't let x be negative 5. That would be one number we don't want. And here you can see 4 minus 4 would be 0. So we can't let x be 4. And so those are the only two numbers we really have to avoid. Anything else is fine. It's okay for the top of the fraction to be 0. So if you use 0, that's okay, because 0 on top is okay. We're really only worried about the denominator, the bottom. So we want to take up these two numbers. To do this, remember when you do domain, with rational expressions, you take out the numbers. You start from negative infinity for the domain, so we can use anything below these numbers until you get to negative 5, which is the smaller of the two. And we say, okay, we don't want to include negative 5, so we're going to use the parentheses, and we're going to get all the numbers up to, but not including negative 5. Then we want the numbers between, so we're going to go from negative 5 to 4, again, not including, so we use parentheses, so we'll actually include those numbers, and we'll use a union to connect the two pieces. So we have the stuff below negative 5, the stuff between negative 5 and 4. And then we want everything above 4, right? 4 to positive infinity. Because anything higher than 4 is okay. The only numbers that are not okay are negative 5 and 4. And again, union puts those together. So this would be the domain. These are the numbers that we are allowed to use. So when you graph this function, it'll have values for all these numbers, but it won't have a value at negative 5, it won't have a value at 4, because you plug in negative 5, it doesn't work. If you plug in 4, it doesn't work. So its domain, if you graph it, it will be missing these here and these here. That's the domain of this function. Now this one's pretty straightforward because it's already factored for us. They don't always do that, so sometimes you'll get a problem that will look like this, a rational function, sorry, it looks like this, and it won't be factored. All that means is that you just factor it yourself. So we're going to factor this first before we try and figure out what the domain is. Don't really have to worry about the top, I'm really just worried about the bottom. On the bottom here, I'm going to factor this. Since it's a difference of squares, it factors into two parentheses, where one's a plus, one's a minus, and I think about the square root of x squared, which is x, and square root of 49, which is 7, and that's what it would look like. So that would be the factored version of x squared minus 49. So from this, we can see that the numbers x can't be would be negative 7, because we don't want a negative 7 there, so they would make that 0, and 7. We want 7 there to make that 0. Those would be the two numbers we wouldn't be allowed to use. So to write the domain for this one, we're going to start from negative infinity until we hit negative 7. And we don't want to include negative 7, so we use parentheses and then union, jump onto the other side of negative 7, go until we hit 7, which is the next number. So 7, union, and then we go from 7 to infinity. And that would be the domain for this one. So again, you have to figure out what to remove, what we don't want, and then domain is everything else. Now what's that look like? So this is a great example, a great problem to show what this looks like. What do we see when we graph this? Now when you type these in, remember your calculator doesn't have a big division bar, so when you want to make it do a division bar type thing, you have to put a parentheses around the top of the expression and around the bottom. So we're going to do parentheses x plus 7, because that's how it's going to make it graph correctly. If you didn't put the parentheses in here, you definitely get the wrong graph. So parentheses x plus 7 divided by parentheses x squared minus 49. So we're going to close the parentheses so that way I've got the expression like it should be. And then that, when I graph it, you'll be able to see what the graph looks like. And you can see it looks pretty normal until it hits about 7, and then it gets kind of weird. So at 7, what it's doing here is it's saying it can't have a value at 7. So to avoid that, it's going to dive down to try and like avoid that. And it's going to get smaller and smaller and smaller. It'll get closer and closer and closer to 7, but it's just going to get smaller and smaller and smaller, and it'll never quite reach 7. And then on the other side, it's actually doing the opposite. It's going bigger and bigger and bigger. We call this a vertical asymptote. We'll talk more about these as we go into this section. A vertical asymptote is a vertical line where your graph gets really close to that line, but it never quite touches it. And this happens at 7 because your graph doesn't like 7. Notice it also doesn't like -7, but you can't tell at -7 because at -7 it doesn't do a asymptote. Instead, at -7, it's just going to have a little hole, kind of a blip. In fact, if you hit the trace key and you type in -7, you'll see it doesn't have any value, right? It doesn't give a y value because you're not allowed to use -7. Same thing, you type in +7, you get no value. So why did it freak out at +7 but just have a little blip at -7? It has to do with what's on the top here. So you can see on the top we have an x plus 7. So if you think about that, the x plus 7s would actually cancel if you simplify this. So the only thing that's left after you simplify is actually the x minus 7, which caused the asymptote at 7, because that's where you're going to have a problem. So we'll see that when we get more into vertical asymptotes, that what cancels actually matters to vertical asymptotes. But these are the things that rational functions can do. They can have these weird asymptotes, or they can have little missing holes in the graph. So they can have lots of weird things going on. So that's what we're going to really get into mostly in this section, is talking about the types of asymptotes, because they're more than just vertical asymptotes, and how to identify them and how to find them from the algebra. So first off, we'll start with vertical asymptotes. Vertical asymptotes can do you can do a couple things. They can, as you approach the line from the right, you can go up and up and up to try and avoid the line, or they can go down and down and down. As you approach from the left, they can go up and up and up, or they can go down and down and down. Basically, they're just going to either shoot upwards or dive downwards because they're trying to kind of avoid hitting at a value, and they will never quite touch that line. Usually, they're pretty easy to find from a graph. So if you look at a graph, you can usually find what the vertical asymptotes are. You just look for that point where the line shot upwards or shot downwards, and it's not touching there. So you have a line like this. This one's at -4. So this vertical asymptote would be the equation x equals -4. Remember, these are vertical lines, so their equations are always going to be x equals a number, because that's telling you where to put this vertical asymptote. So -4 has another vertical asymptote. There's another one right here you can see. So this one would also be a vertical asymptote. It looks like that's at 1, because I think this is my 0 right here, so it would be 1. So x equals 1 would be a vertical asymptote. Over here, you can see this is actually 1 as well. It's right here. You can see that these both are going up. There's no rule about one goes up, one goes down, so they can both go up, they can both go down. You can have one go down and one go up. They can do all kinds of things. So this is, anything's pretty much possible. So that could happen. And so yeah, this one would have a vertical asymptote x equals 5. So those would all be vertical asymptotes. Those would all be vertical asymptotes. An equation can have more than one vertical asymptote. It's definitely possible. So you could write an equation that has 2, 3, 4, 5. There's some weird equations you don't really see until trig class that have infinitely many vertical asymptotes. That can happen. So we don't really see those in this class, but that's what it looks like. And from a graph, they're usually pretty easy to identify. So if you can graph the equation, most of the time you can just use that to find them if you need to. Now, without graphing them, you can still also find the vertical asymptote using this rule right here. So the rule says that if you have a function that's p over q, so it's a rational expression because there's something on top, something on bottom, it says that if there's no common factors, so no common factors means it's simplified. We saw earlier we wanted to simplify. So if there's no common factors, so it's simplified, and a is a 0 of the bottom, then x equals a is a vertical asymptote. So basically, I want you to do no common factors. I want you to simplify first, and then find the zeros that are still there, the ones that don't go away when you simplify, and those cause vertical asymptotes. The ones that do go away when you simplify, those are just going to cause holes. That's the big difference. So it's the restrictions, or the numbers you're not allowed to use, restrictions that don't cancel. And that's what causes the vertical asymptotes. The restrictions that don't cancel. So for like this first example, first thing you want to do is you want to simplify before you do anything else. Since this is already factored, we can go ahead and start canceling. You can see that the x's would cancel, and this expression would just become 1 over x plus 4. So since the x is canceled, we're just left with the x plus 4 in the bottom, that's going to be the restriction that causes us to have vertical asymptotes. The vertical asymptote is going to happen at -4, because -4 plus 4 would be 0. So x equals -4 would be a vertical asymptote. Note that this x that canceled was also a restriction, right? There's an x on the bottom. So if you put 0 in there, that would make the bottom equal 0, because 0 times anything would be 0. So that x equals 0, that is actually a whole, not a vertical asymptote. So it's just going to be a whole. So this is going to be like when we graph the one on the, with the x plus 7, x minus 7. You have one where it's just a whole, where the graph looks like normal, it doesn't do the vertical asymptote thing, and then one that actually is a vertical asymptote. And it's all about the one that was still there after you simplified. Now that one was already factored for us, so a lot of times when you want to simplify these, you will have to factor them yourself. So let's go ahead and do this one. First thing we'll have to factor. So we're going to do that first. We'll factor first. So leave the x minus 3 alone because that's already factored as much as it can. But the bottom is another difference of squares, which we can factor into x plus 3, x minus 3. Remember, difference of squares plus or minus, and then square the first thing, square the last thing. And that's how you get the difference of squares factoring. Here you can see the x minus 3's simplify, they cancel. So you're just left with 1 over x plus 3. So this tells us that the vertical asymptote comes from that expression. The vertical asymptote is going to be x equals -3. So it's going to be -3 because -3 plus 3 gives us 0. That's going to be the vertical asymptote. So the whole in this case, they don't always have to have a whole, but in this case, the whole would actually come from the x minus 3 because that's the part that canceled. So x equals 3 would be a whole. So they don't always have a whole because you can have an expression where nothing canceled and you just have vertical asymptotes. So that can happen. But if they do have a part that cancels, that's going to be the part that would just give you a whole. And I don't think your homework actually asks you about the whole, so that's kind of good to know that they exist and that that's what happens to the other part. Because all the restrictions matter, it's just that the restrictions that don't cancel are the ones that actually give you vertical asymptotes. So that's where vertical asymptotes come from. They're restrictions that won't simplify away. We saw previously with these rational expressions, you always have to worry about all the numbers that make the bottom 0. But in this case, the ones that give us vertical asymptotes are just the ones that don't cancel. Those are the ones that are really important for the shape of the graph. Okay, now we talked about vertical asymptotes. So that gives you the idea that there's probably other kind of asymptotes, right? And there are. The next type is called horizontal asymptotes. Now, horizontal asymptotes are a little different. They're not a line that you can never touch vertical like that. They are a horizontal line that you approach. The reason they're different is because horizontal asymptotes have more to do with what happens as you go to left or right towards infinity, which is another way of saying as x gets really big, either really positive or really negative. So basically we're talking about what happens at the ends of the graph. Now, if you think back to our other equations, the things we've worked with so far, like quadratics and cubics and all that stuff, if you look at the ends of those, what they end up doing is they actually end up shooting up to infinity or down to negative infinity. All those parabolas either opened upwards to infinity or downwards to negative infinity. The linear functions, usually the diagonal lines, will go up and down to infinity. With rational expressions, they don't always go off to infinity. Sometimes they level out. They'll hit close to a certain value and then they'll just kind of peak, and they'll never get any higher than that value. They'll get closer and closer to it, but they'll never quite reach it. That can happen with rational expressions, and that's what we call a horizontal asymptote. It's actually a horizontal line that at the ends of the graph is getting closer and closer to that value, but not quite touching it. So here they show you a couple different examples, like you might have this line B, and you might get closer and closer from the bottom and never quite touch it. Or you might get closer and closer from the top and never touch it. But you're not going to touch it at the end. At the end, you're going to get closer and closer but not touch it. Now, it is okay to cross a horizontal asymptote somewhere in the middle. Not at the ends, but in the middle. So somewhere in the middle, you might cross it, and then as you go off to infinity, you'll get level off and never quite reach it. So it is okay to cross them. You can cross them, but only in the middle area. At the ends, you can't. So that's something about horizontal asymptotes. So horizontal asymptotes, it's what you approach. You approach it as x goes to infinity, either positive or negative. That's the horizontal asymptotes, the line that you're getting closer and closer to at the ends. Again, you can see these from graphs. So you can kind of see here this one. This one, as you get closer and closer from both sides, you're getting closer and closer to 2. So this one would be the line y equals 2. That would be your horizontal asymptote for this one. Over here, this one, I've had students in the past say, are there 2? And the answer is actually there's not. There's only 1. It actually is a rule that you can only have 1 horizontal asymptote. There's no way to have 2. So I know this one almost looks like there's 1 up here and 1 down here. If you just draw this graph out further, left and right, you'd see that they actually get really, really close to 0 because they're both going to get closer and closer to the middle. I had to cut the ends of the graph off to make it fit on my paper, so that's why it looks like there might be 2. There's actually only ever 1, so this horizontal asymptote for this one would be y equals 0, which is a pretty common horizontal asymptote. A lot of things get close to 0 at the ends. So horizontal asymptotes, there's only ever 1, and in the middle they can cross. It's okay to cross in the middle, but at the ends you're getting closer and closer to the value without crossing. Okay, now how do you figure out what the horizontal asymptote is without looking at the graph? Well, what you do is you actually look at, if you have a polynomial, this is just kind of a generic way to write a polynomial, you look at the degrees of the leading coefficients, the highest degree at the top and the bottom, and you compare those. And which one's bigger actually tells you what your horizontal asymptote is going to look like. So first off, if the top is smaller, so if the bottom is bigger, so this is, top is less than the bottom. So that's the first option. If that happens, top is less than the bottom, then the x-axis, or y equals 0, is the horizontal asymptote. Now, why does that happen? Well, let's look at this example down here. This one, you can see the top, n, is 1. The bottom, m, is 2. So that'd be the degrees, right? Degree 1, degree 2. And since n is less than m, 1 is less than 2, this one is actually going to have y equals 0. Now, why is that? Well, think about what happens as x gets really big. As x starts off at 10, 100, 1,000, and then it gets on to tens of thousands, millions, billions. Notice that on the top, you'll only ever have 15 of those. So when you get to a billion, you have 15 billion. On the bottom, you actually have a billion squared. You also have another 9 billion over here, but when I talk about million billion squared, that's like a billion billion. You really kind of forget about this 9 over here because, if I have a billion billion and you take away 9 billion, I don't really care because 9 billion, 9 billion is not that much when I have a billion billion. So what we do is we kind of ignore everything smaller in these leading coefficients, these leading, terms, and we look at the degrees there. And if the top is smaller, what happens is the bottom number is actually going to get bigger faster. Because on the top, when x is a billion, you have 15 billion. But on the bottom, you have 3 billion billion. And that's just a billion. If I think of like some numbers that are bigger, like a trillion, a quadrillion, whatever, something way bigger, then on the bottom you have squared times that versus the top you only have 1 times that. So you can see how as the number gets bigger and bigger and bigger, the bottom is always going to be getting bigger faster. And what happens to a fraction is when the bottom gets bigger and bigger and bigger, the fraction gets smaller. So think of numbers like 1/10, 100th, 1,000. As the bottom gets bigger, you're getting a smaller and smaller piece. So the bottom blows up to infinity, the fraction gets smaller and smaller and smaller, closer to 0. So if the degree on bottom is bigger than the degree on top, so the degree on bottom is bigger, the bottom blows up, so the bottom increases faster, it gets really huge. So the fraction goes to 0. And so this one, y equals 0, is the horizontal asymptote. So that's what happens. If the degree on bottom is bigger than the degree on top, so the top one's smaller, that's when you get y equals 0 as a horizontal asymptote. And the next one's a little different. This one, the two are equal. So what if the bottom and the top are equal? They're the same size. Well, in this case, you actually get a fraction of the leading coefficients, the numbers in the front. Well, why does this happen? Why is that your horizontal asymptote? So think about this case. Again, as x's get bigger, we're not really going to worry about the small stuff, because when x squared is huge, or, when x is millions, this is millions of millions, and that's just 1 million. And who cares about 1 million if you have millions of millions? Now that sounds weird to think about. Who cares about a million? But if I have millions of dollars, and you take away $1 million, I don't care. So this other stuff stops mattering. And really all we look at is the first part. And we say, okay, well, the top and the bottom have the same degree. So the top is 5 million millions, but the bottom is 3 million millions. the label's the same, so you can pretty much just cancel the x squareds because they do match up. And so you can really just look at the coefficients in the front and say that the top is always going to be 5 of these millions and millions. The bottom is always going to be 3 of these millions and millions. So you always have a little bit more on top than on bottom. So that fraction, that ratio, is what you're going to be getting closer and closer to. Because the bigger the x gets, the less these other small stuff will matter. So you're going to be getting closer and closer to that fraction. So y equals 5/3 is going to be our horizontal asymptote in this case. Because you're always getting closer to that ratio of these leading coefficients. And again, that's when the degree matches. N is 2 and m is 2. And 2 equals 2, right? So n equals m. They're the same degree. So the degree matches. You just cancel everything out except for the leading coefficients, and that's what you're getting closer to. Okay, third option. What if the top is bigger? So what if the top is bigger than the bottom? In this case, there is not a horizontal asymptote. So a problem like this, where the top is bigger than the bottom, again, you're going to ignore all the small stuff. This stuff's not really going to affect things. You're really just going to look at these first two. But you're going to look at those and you're going to say, oh, the degree on top is bigger, so the top is blowing up. It's getting bigger faster than the bottom. Because again, the bottom, if I have 1,000, this is 1,000 squared, so thousands of thousands. But the top is thousands cubed. So it's thousands times thousands times thousands, which is much bigger. As you get to millions, you have millions and millions and millions. So the top is getting bigger faster. So in this case, when the degree on top is bigger, so n is 3 and m is 2, and 3 is bigger than 2, so the top is bigger than the bottom. In this case, the top is increasing faster. So the fraction is going to infinity. And it might be going to positive infinity, it might be going to negative infinity. It all depends on the signs and stuff. We don't really worry about that. We're just going to note that since it's shooting up to infinity, either up to infinity or down to infinity, it's not leveling out. So there is no horizontal asymptote. Because to have a horizontal asymptote, you have to level out. You have to get close to a specific value, close to a number like 5/3 or close to 0. But if you're going off to infinity, you're not leveling out. In fact, all those things we've dealt with earlier, the linear equations, the quadratics, the cubics, stuff like that, they all didn't have anything on the bottom. So of course the top is bigger than the bottom, which is why all of those shoot off to infinity, because they didn't have horizontal asymptotes. So that's always true for anything that doesn't have a bottom. It's not a rational expression. It has to shoot off to infinity. It can't level out. Okay, that's the two main types of asymptotes, and those are the two types I'll probably test you on. There is one more, and it's going to be mentioned in your homework, so I just want to make sure you're aware of it and know how to deal with it. It's not as important, so we're not going to see it as much. I want to point it out. And again, this is on the homework. This is called a slant asymptote. So the third type of asymptote is a slant asymptote, or a diagonal asymptote. Oblique is the word your textbook uses. This says that at the ends of the graph, it actually gets closer and closer to a diagonal line, to like a straight line kind of thing. Now, this only happens if the degree of the numerator, so the top, is exactly 1 more than the degree of the denominator. So if you think of the numerator and top, and then the m for the denominator and bottom, it says the top is 1 more than the bottom. In other words, the top is bigger than the bottom. So this only happens in the last case previously when there's no horizontal asymptote. So in other words, you can't get closer to a diagonal line if you're leveling out, right? If you're leveling out getting horizontally even, then it's not going to go off to infinity, so it doesn't work. So this only happens if there's no horizontal asymptote. So if you find a horizontal asymptote, then don't even bother with the oblique or slant. It doesn't exist. It can't happen. You only check for this if there's no horizontal asymptote. Once you've established there's no horizontal asymptote, then you can look at the degrees. Here I have degree 2 on the top and degree 1 on the bottom. You look at the degrees, and if the top degree is 1 more than the bottom, then you check for slant. So 2 is 1 more than the 1 on the bottom. That checks out. Now we have a slant or oblique asymptote. Now, how do you find the slant asymptote? What you do is you find the slant by doing the division and dropping the remainder. So if you want to find a slant, you just do the division. Just take this problem, actually do the division, and just ignore the remainder. We don't use the remainder. And what the rest of the stuff is the slant asymptote. I'll give you ones that you can just use the synthetic division. You don't have to worry about long division in the homework and stuff. So this is what you would check for. Is you check for this and you look at the synthetic division. We always take the x minus 2 and turn that into a plus 2 as your divisor. That's what you're dividing by. On the top, we have the coefficients 1, 2, and negative 1. And then we do a box with our remainder. Again, we don't really need the remainder. We're going to drop it anyways. I just like to put it there because it's habit. Add, multiply, so 1 plus 0 is 1, 1 times 2 is 2, 2 is 4, 4 is 8, negative 1 plus 8 is 7. I drop the remainder, because we don't want that remainder, and I just look at what I have. So I have 4 as my constant, 1 is an x, so my answer is x plus 4. That is the oblique or slant asymptote. So oblique or slant asymptote, it really, you just do the division and drop the remainder, and then you got it. But this is only in cases where you can do this back where the top is 1 bigger than the bottom. So you're always looking for the top and the bottom. So again, we're looking at these first two, just like the horizontal asymptote, and the top has to be exactly 1 more than the bottom. Otherwise, this doesn't work. Okay, like I said, don't worry as much about the oblique asymptote. I really want you to be ready for vertical and horizontal asymptotes. Those are what you'll really see a lot of on like the quiz and the exams, the vertical and horizontal. Okay, last thing, I'm just going to take all this and we're going to put it together. We're going to graph a function. Now we could throw it in our calculator, but we're going to try and do it without, because knowing how to do all these steps is what you should be ready for in the exam. You should be able to find things like the vertical asymptotes, the horizontal asymptotes. You should be able to find zeros of these rational functions. We'll talk about how to do that. Find f of 0, which is your y-intercept. It's always nice to know what the y-intercept is. And then other values as needed. So we're going to graph this one. First off, we want to find the vertical asymptotes. Remember, to find vertical asymptotes, you need to factor. So I'm going to factor this into 4x over, well, this factors into x minus 2, x plus 2. Again, that's a difference of squares, so you just factor into the plus or minus thing. Here, nothing cancels, so we actually get 2 vertical asymptotes. We get one at 2. And one at negative 2. So first off, first thing we know is this has vertical asymptotes. So these are always x equals equations, right? One at negative 2 and one at 2. So x equals negative 2 and x equals 2 are the vertical asymptotes. So again, those are restrictions, things that we that don't cancel. So you always should be able to find those vertical asymptotes. Next, you want to be able to find the horizontal asymptote. Remember the horizontal asymptote? You look at the degrees. In this case, the degree on top is 1, the degree on bottom is 2. So 1 is less than 2, or the top is less than the bottom. And so this one, it's actually y equals 0, because the top is less than the bottom. Whenever the top is smaller, remember it's going to get close to 0 because the bottom's going to blow up. So this one has a horizontal asymptote at 0. Remember, that means that at the ends, you're going to get close to but not quite touch this. You can cross it in the middle. It's okay to cross in the middle. But at the ends, when we go off to infinity or negative infinity or infinity, you're going to get close to this line but not quite touch it. And that's the line y equals 0. That's our horizontal asymptote. Now, we saw that it has a horizontal asymptote, so we don't have to worry about slant or oblique, right? Because once you have a horizontal asymptote, you can't have a slant or oblique. It has to level out because it has a horizontal asymptote. Next thing we want us to find the zeros, which are the same thing as the x-intercepts, because x-intercepts are zeros. So we're going to find the zeros. We don't really care about the non-real zeros, the ones that wouldn't be x-intercepts, because they won't show up on the graph anyway. So we're just worried about the real ones. To find the zeros of this, so we want to find the numbers where this will equal 0. So I'm going to take 0 and set it equal to the function, 4x over x squared minus 4. Now note, there's something important to notice about this. The only way you can make a fraction equal 0 is if the top equals 0. You can't take a fraction and make the bottom equal 0, because remember, you're not allowed to make the bottom 0. That's restrictions. We're not allowed to do that. And the only way you divide and get 0 is if the top number is 0. So I really don't set the whole fraction to equal 0. I'm just going to set the top equal 0. So if you want to make a fraction equal 0, you just set the top equal 0. So we'll actually find the x-intercept just by doing this. Divide 4 across, and you see that 0, because 4 is 0 divided by 4 is 0, is the x-intercept. So the x-intercept is 0. And that's how you find the x-intercept. You just set the top equals 0. So set top equals 0. And that's how you find the x-intercept when you're doing x-intercepts. Y-intercept, that's just when you set 0 or x equal to 0. That's how you find the y-intercept. So we're just going to do f of 0. That's how you do the y-intercept. So I take my expression, my 4 times 0, because I'm replacing x with 0, over 0 squared minus 4. And then you just simplify it, solve that out, see what you get. So 4 times 0 is 0, so you get 0. 0 squared is 0, minus 4 is a negative 4. But 0 divided by anything is 0. Well, of course, we already knew that because if this is the x-intercept, it's also the y-intercept, right? Because it's the middle and crosses both the x and the y-axis. So if you were paying attention, you might have figured that out before I even did this. But they don't always do that. Sometimes you'll have a different y-intercept than you do an x-intercept. So it's good to know how to find both. If you're trying to find the x-intercept, you set the top equal to 0. If you're trying to find the y-intercept, you replace x with 0, and that's how you find the y-intercept. Okay, we know it crosses here, and that's the only place it crosses because that's the only intercept. We got these values. Last thing to do here is to graph this. We're going to have to find some other function values. So we're going to have to plug some other numbers in and see what happens. So what I would probably do if I was working on this one is find other function values. And basically, I'm going to look and see what happens in between these different lines. Because I know when it gets close to these lines, these vertical lines, either that has to go up forever or down forever. So I got to figure out what's going to happen there. So I got to figure out, is it going to be above the line or below the line? I'm going to do that by just finding some values. I'm going to find things like f of 1, and that'll tell me what's going on here. If it's up here, it goes like this. If it's down here, it goes like that. I'll do things like f of 3 to see if it's doing that or that. So let's do like f of 1. Well, f of 1 would just be 4 times 1 over 1 squared minus 4, which is 4 over 1 squared is 1 minus 4 is negative 3. So that'd be a negative 4/3, right? 4 over negative 3 is negative 4/3. So at 1, it's going to be down 4/3. It's going to be 3/3, 4/3. It's going to be right here. That's going to be that point. Let's do f of 3, see what happens at 3. So we get 4 times 3 over 3 squared minus 4. Well, 4 times 3 is 12, so you get 12 on the top. 3 squared is 9 minus 4 is 5. Is that right? 12. And 3 squared is 9 minus 4 is 5. 12 fifths. Okay, 12 fifths. Well, 5 fifths would be 1. 10 fifths is 2. And 12 fifths is going to be like 10 and 2 fifths. So, and it's going to be about here. Not quite half. So there's a point there. That's actually enough to do this one, really, because now we know that this line, since it has to get closer and closer to this line, it's going to go up. Now, why do I know it's not going to go back down? Well, because the only x-intercept's right there. So this line has to go up because it can't cross this axis. It's going to go up as it gets closer and closer to this vertical asymptote. On the right side, it's going to get lower, but it's never going to quite cross the horizontal asymptote. So this is what that piece looks like. Over here, this piece, I can see these are going to connect, and then this one, again, it can't go back up because the x-intercept's right there. So it has to keep going. So it's going to go downwards and go like this. Now, how do I draw the rest of the graph? 2 ways to do it. One, I could plug more numbers in, so I could do f of -1 and f of -3. The other way to do it is actually use symmetry. Remember we had those symmetries in the past? This graph actually has symmetry. If you plug in negative x, if you do f of negative x, then you get 4 times negative x over negative x squared. Sorry, negative x squared should be inside that. Minus 4. And on top, negative 4 times negative x gives me a negative 4x, but on the bottom, the negative x squares, so we just get x squared minus 4. And you might say, well, that's different than the original, and it's not, it's not the same. So that's not even, I agree, but this actually is opposite, because you can see how this one, if you take a negative times this fraction, you only multiply the -1 times the top, not the bottom. That's how fractions multiply by -1, and you get this. And this is the opposite. It's opposite. It's opposite. And so since it's the opposite, this guy is actually going to be odd. It's going to have rotation symmetry. If you don't like to look at symmetries, I think this is just kind of a cool way to do it. If you don't, you can just find more function values. But what you'll see if you find more function values is that when you do -1, instead of getting a negative 4/3, you get a positive 4/3. You actually get a number right here. Because what's going to happen is it's going to have a symmetry where when you go on this side, it's going to go like this. So that when you rotate it, it'll look the same either way. Because it does have that odd symmetry. Same thing, this piece up here is going to have a matching piece down here. So we're going to negative 3, I'm going to go down 10, 11, 12 fifths, and have a piece that goes like this. Because when you do symmetry, it's going to match. So this function has the odd rotation symmetry. Now, again, you don't have to use symmetry. You could just found f of negative 1 and found out that's positive 4/3, and f of negative 3 and found out that's negative 12 fifths. And that's how you could have gotten these 2 points. So you don't have to use symmetry to do those two. But if you did use symmetry, yeah, you notice that this is odd, then you can use rotation symmetry. Again, I'm not really going to ever test you or make you use the symmetry on this stuff. Really, I just want you to be able to find the asymptotes. It's good to know how to find the intercept. And then, if you want to graph this by hand, you have to plug in the values. Now, if you want to, you could type in your calculator. Just be careful when you type this in your calculator, you type it in correctly. You always want to put parentheses around the top and around the bottom. So that way it goes in correctly and you get the right answer. So that's what it would look like when you type it in, and when you graph it, it should look like that. And so now we can see we did it right. You can see how it has that symmetry and all that. It doesn't show you the asymptotes, but you can see how there's going to be a vertical asymptotes there and a horizontal asymptote there. Okay, so the big thing from this section, I really want you to be ready to find your vertical asymptotes and your horizontal asymptotes, and then know how to write those as equations like this. And that's it for Unit 2. We are done with Unit 2, so you got that test coming up, and then after the test, we'll start into Unit 3, our last unit. We're getting closer to the end of the semester, so hope you are doing well and are getting ready for that test.